Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're going to go ahead and start. Before I do, I'd like to get a feeling for, since I've exchanged email with some of you, maybe even more than some of you, but I don't necessarily know faces. So what I would like to do is get a feeling for where people are from, because I know there are people. Here from SQL. There are some folks from Office and Windows. CLR was also interested. So I'm not too sure. We just so Stathis, I know about you. Just say your name and tell me what division. What are you working on?
James Salio, I work for Banner.
Oh, yeah. Okay, fine. Nice to meet you.
Eric Stetson, Windows Networking.
Okay, great. Eric, we exchanged email.
Waldo, I'm on CLR.
Wonderful. Very good. Okay.
Alan Wilson, MSIT Enterprise Architecture.
Very good. Okay. So Hazem, I know.
Hazem Shafi, Developer Division Performance.
Okay.
My name is Fado. I'm from Operations Manager.
Okay.
Capacity Planning and Capacity Management.
Great.
I'm Wayne Cranston from Exchange Server.
Exchange Server. Okay, excellent.
Jeff Kay, also from Exchange.
Wonderful.
Dean Dribble from Midori Incubation.
Okay, good.
Deb Callahan. I'm in a team in Visual Studio looking at Parallel Computing.
Okay, very good. Okay. Yeah, go ahead and introduce yourselves, even though we'll move back.
Oh, I'm Ryan Stonecypher from SQL.
And I'm Ashit Basale from SQL.
Gaurav, SQL Performance.
Good.
I'm Guru Muxamandra of SQL.
I'm Peter Engar from Office.
Daniel, MSN Search.
Okay, good.
John Richardson from Midori, formerly Windows.
Okay.
Marius from Hotmail.
Nice to meet you, Mario. Mario got in touch with me early on when I got to Microsoft and has been doing work with Hotmail. Okay. So you're the last one and you get to introduce yourself.
I'm Sean Cox with Office Communications Server.
Great. Okay. So I'm Joe Hellerstein, Developer Division, been here for about 7 months, and then before that I was at IBM for 20 plus years. So what I'm going to do is I'm going to talk about work that actually originally started at IBM. I was in the research division, and it ultimately led to a couple of performance features in DB2. And we started this out as sort of a science experiment, trying to understand what would be the value of using control theory to do a resource management design. And we found a lot of value in it. So what I'm hoping you'll see today through both a combination of some examples and trying to understand some of the theory behind it is how you might go about using this in your projects. You should be able, when you come out of here, to have enough depth of understanding that you appreciate what the techniques are. And I think you'll actually be able to apply it in some modest cases. But there's going to be some work to go from there. And so I hope you get to the point where you can make an informed decision about whether or not this is something you want to do. And frankly, what I'd like to do is work with you. We'll see how many people are interested. I don't scale that far. But I'd like to be able to get to the point to see if there's some value here. Okay, so what I'm going to do is I'm going to actually present this sort of from a historical perspective and give you a feeling from where we started and give you a feeling for some of the techniques. And then I'm going to go through and I'll actually give you a certain amount of technical background so you can understand how to actually apply some of the control theory techniques. So where we started was we were initially looking at something that was problematic for us several years ago. Actually, it was something that Ray Ozzie worked on before he left IBM, went off and did other things, ultimately ended up here, an email server called Lotus Notes. And the problem was, at that time, the server was capable of modest groupware kind of activities, but it was very problematic when we scaled up to about managing about 300,000 employees. And so what we found was that the operations staff, to make sure that the server didn't topple over, was managing its load manually. The way they did this, the interaction with the users was through RPCs, and what the operations staff would do is they would control, ultimately they wanted to control the number of RPCs that are being processed concurrently, essentially the number of users that were active inside the server, measured in terms of RPCs that were concurrently present. There was no knob that did that. And so what they did have a knob for is they could control the number of connected users. And it basically, the abstraction for Lotus Notes was a database kind of metaphor. You could control connections to the database. And what would happen is that max users parameter would determine the point at which you transitioned from allowing more users to come in, essentially admission control kind of thing, until you wouldn't. And then there would be basically a retry forced back on the client. So that's what the administrative staff was controlling manually. I apologize for this cartoon, but the idea was to insert something in between there that would do it automatically. And my background is not control theory, but I started working with a mechanical engineer at University of Michigan, and she looked at this and she said, this is relatively a simple kind of thing. Here's what you should do. This server is really what we call in control theory a plant. What the controller is going to do is it's going to look at the difference between some desired level of RPCs, or RPCs in system, and the actual level that you're measuring. And look at that difference. That difference is called the control error. And the controller, what it's going to do is then figure out, based on that control error, what you should set max users at. So if your desired level of RPCs, based on what your experience is for what the server can handle, is larger than what you're actually seeing, you're going to increase max users. And if it's smaller, or it becomes negative, that difference is negative, you're going to decrease it. And that's what this controller does, and there's some various standard things that people in control theory, like mechanical engineers, do. So, we went ahead and did that, and we found that we got a number of benefits from working that way. One of the biggest benefits was that as a result of doing this kind of thing, we could actually analyze what the system behavior was without running a lot of experiments on individual controllers. And so that proved to be a big advantage. The other thing was it gave us a way of sort of understanding certain characteristics of the system which were crucial to its control performance that we didn't appreciate at the onset. So for example, the way we were measuring the actual RPCs in system is there was a log that got written every time an RPC completed. And we didn't see the RPC until that log was written. So once the RPC completed, the log was written what the arrival time was and the departure time. And so then you could either get compute by looking through the log, RPCs in system, or you could response times or various other things. The problem with this is that measurement, measuring it that way, introduces a delay. Because you don't know anything until the RPC completes. The longer the RPC takes, the more the delay. The impact is then that the controller has stale state about the server. And as a result, the controller can take actions that are not reflective of the server's current state. All that ends up getting reflected in the way people do analysis of control systems, and it's very helpful in terms of appreciating some of those implications. Okay, so what I was going to do, yeah, please.
I don't know if you're covering that later, but why control theory? I mean, why do you have to control? I understand there's a scaling issue and things like that. I mean, shouldn't it be the last option that you should be exercising?
And so why control theory, or why are you saying why control it?
Why control it? Why control the number of users? I mean, shouldn't it be the last option? I mean, this is specific to very specific scenarios like email server where the latency is not an issue as much.
Right. So the question is why do you want to control the number of users? I think admission control kinds of problems are pretty common. There may have been, ultimately what happened was there were changes made to resource management in the servers, but this was a problem that the operations staff was having, and there wasn't a ready solution.
You think it can be applied to other situations other than?
Well, I mean, there's admission control in networks. I mean, there's lots of cases where this kind of thing comes up. It's not unique.
As opposed to what? I mean, you're saying why do this as opposed to what?
As opposed to trying to scale the application, trying to see if we can go to multiple servers, have a web farm, etc.
In my experience, Office Communications is a real-time server where latency is actually what we measure and try to control. What we find is if you don't apply control, then you quickly get into the dynamics of a queuing system where you hit that knee of the curve and response times just exponentially increase, and your server will take a long time to recover. So it's not a question of scaling the software. I mean, at first it's a question of scaling the software, but you're invariably going to run into a limitation, either memory, CPU, or disk. And when you approach that point, you want to be able to run flat and utilize the resource to its fullest extent while bounding some other metric that you care about. Sorry,
No, that's great. I mean, part of the challenge to me is that people, I don't know people in advance, and they come in with, different interests, and so being able to level set quickly is helpful. I appreciate that. Thank you. Okay, what I'm going to do on this slide is try to give you a feeling for what, sort of the next level of detail about these techniques. And then we'll sort of go from there in terms of giving you the background to fill in some of the gaps on this. Because I want to try and get you a sense about how this works. Okay, so I'm going to take this example, and again, I admit it was a science problem, but it's sort of a science project, but it gives you a feeling for what all is involved. Here's how my colleague at University of Michigan went about helping us with figuring this out. So she said, look, what you've got here as a very simple loop is, as I mentioned before, there's this measured output we've got over here and this desired level. I mean, typically we're looking at like at 200 RPCs in the system was a reasonable desired level. We've got this measured output from the server log over there, and you take the difference, and that's the control error. So that's this thing up there. Then the next thing we've got is the system itself. In this case, the server. In control theory, they call it the plant. Now, what you need is some expression that relates how you set max users, which is this admission control parameter, to the effect on RPC instance system. And this could be a very complicated thing, especially if you look at it from the point of view of like a capacity planning kind of problem where you want to try and do this in advance and forecast, weeks or months in the future. But for control, if you are making changes on a periodic basis, you can have potentially relatively simple models, and the fact that you're constantly adjusting and adapting will sort of compensate for that simplicity. And so the guidance she gave us from her experience as a mechanical engineer, and it's a lot of nonlinearities that she's had to deal with as a mechanical engineer, like turbulent fluid flows and things like that, said, look, this is a simple, what the term is first order model, because it relates the YK, which is the actual RPC, that's what you're measuring. That's YK, that's the measurement at time K, so like at 2 o'clock. Saying that that's going to be some constant, which you're going to have to figure out. I'll show you how we figure it out in a second. Times what it was at 1:55, like if you're doing 5-minute intervals, or 1:59, we were doing 1-minute intervals, plus another constant times the effect of max users. And intuitively what's going on here is that you're saying that the current state depends on the immediate previous state plus what the control is. That's the intuition. Extremely simple. It's linear, it's deterministic, all sorts of things wrong with this model. Okay, just let me finish this one thought and then I'll get to you. There's a famous statistician, his name is George Box, and he had a comment about these kinds of models. He said, all models are wrong, but some are useful. And I think that's been the general experience. In any case, please, questions?
So I realize it's a simplified model, right, for the system, but in reality there's always some term there, which let's call it noise or something like that, or some external factors you can't control. And in case in point here, it's possible to allow more users in the system, to connect to the database, so to speak. But once they connect to the database, they're already connected, and they can do maybe very heavy load. So how do you go from there? Like, it's maybe like a more leading question towards how can you know that the input can really control the output with enough correlation going both ways up and down so that the system is effective?
Okay, so let me repeat the question because it's a very important question, and it's actually one of the fundamental ones you always have to face when you're looking at this kind of control. So there are actually, I think, a couple of questions. One of them is, does this kind of model, does it remain constant over time? Might something change in the system? You change in the workload, a change in maybe there's a failure, and maybe those relationships are not the same over time. And the second question is, what happens, how good of a model can you actually come up with? How close will that connection have to be? Okay, so for the first part, does it change over time? Yeah, it absolutely does change over time. There's a certain amount of robustness with this because the controller makes changes as well and sort of compensates for what's happening in the server. But ultimately what we ended up doing in the real world examples, like what we've done with DB2, is we don't use this kind of static model. We use something called adaptive control. And we actually calculate these constants on the fly. So I think that's what happens in practice. Now, this has some extra challenges as well because that becomes another form of feedback. You have to be careful about that. The other part is, how accurate does this have to be? I don't have any way of quantifying this, but I can tell you historically the reason why control theory was developed, actually with a lot of this came out of, well, part of it was World War II and stuff that even preceded that with just like development of milling processes, was that they found that the machines would wear, and over time the relationship between the controls and the effects of these machines varied. And the advantage of these kinds of models was they seemed to be self-correcting because of the controller, even if the model was not as accurate as you would like.
So I think you can get a model that's probably not accurate as long as you can have continuous time feedback and you adjust the input, so to speak, the system. That's probably one problem, which is somehow correctable. But the other problem is, how do you know by correcting the input, the output, you can actually correct the output. You can vary the output.
Okay, so the effect. This a different question is, how do you know that the control is effective? Essentially, that the input is going to affect the output, right? And that's
some amount you can always control the output to some degree, but sometimes.
Okay, and that's fair, and that's actually a system design issue that we try and deal with up front. Okay. All right, one other question I want to press on.
So when you use this equation yk is equal to some constant into yk minus 1, aren't you assuming like an exponential decay model where, with time, the effect of
right. I mean, that's right. And what this means is that under basically no additional input, so if you just have the system in some sort of steady state and you change that input, here's how long essentially it's going to take to settle. That's really what it means.
Is that always true, or does that work? It doesn't matter.
It depends on the nature of the control. I mean, we've had reasonable success with this. I mean, there are other variations on this. There are more complicated models you can use, but the amazingly simple models seem to work pretty well. Okay, so what I'm going to do is, and this is good background discussion, there is, in the materials that I sent out, there's a spreadsheet, and let's see how much of this is helpful for the folks here. I know I've taught this at Columbia University, and I know that for students there, this kind of exercise was helpful for them. What I'm going to do is give you a more detailed feeling about how this works. Okay, so what we've got here, we see the control diagram over there. I've got a spreadsheet over here where each one of the columns here corresponds to these letters. Really, the data are what are called signals flowing through. So we've got RK or E of K over there, and there's the R to the left, which I can't show. Limited. Well, I can. Yeah, somewhat limited screen space. Let me at least sync up with that. I can do that a little bit. Okay, so at least we can sync up on the diagram, and then later on we'll do the without. All right, so so K is time, discrete time. R is in this, it's a constant over here, like a 200. Over here, we allow for a capability where R could change with time, but really only deal with constants. E is the difference between R and Y. We've got U, which is the output, and Y, which is the measure, or the U is the control input, and Y is the measured output. Okay, and then this is the set of equations that are used to describe this based on the models that we've got there. Okay, so what I'm going to do is play with this a little bit to give you a feeling for some of the control design issues. So if we look at this, we can just go across here. Let's pick this roll here. So this is a constant that's picked up from that column G9, which is where the R is, the reference value. And then as we move across there, this is just the difference of the reference value from the measured output. So you look at the B column minus the Y column. So this is the U that's the U value, and in this case we have a relatively simple kind of control that just says, okay, I'm going to take some constant and multiply it by that control error, and that's going to determine my U value. This is actually going to have to be a normalized value, is the way to interpret it for this simple example, because otherwise when E is negative, you get negative users, which doesn't make any sense. So think of this as some sort of normalization. You've got some reference value, and you're going plus and minus that reference value that for number of users. Like you want to have it at 200, and a minus 10 means really 190. So just for the purposes of this example. And this is the output from the system, and you can see that expressed as this equation up here, which corresponds to that over there. It's basically these coefficients. So that was 0.43 is what you multiply by the last Y value over here, and then 0.47 is then what you're going to multiply by that control. All right, so that's the system. Here's a plot of it. The design problem is to pick this constant, Kp. And basically what it's saying is, let me go back to the diagram so this makes more sense. The controller design problem is pick a Kp so that we end up with the measured output be equal to the reference value. That's what we want to do. That's the design problem. Does that make sense? Okay. So, you've been in this class for 15 minutes. Let's figure it out. Okay, well, obviously right now we're going to do it by trial and error. All right, so 1 is the starting point. Okay, now, so what are our design criteria? What do we want to try and achieve with this? Okay, well, one thing is we'd like the measured output to be equal to that reference value. So we set the reference value at 200 for the number of users. That's what we'd like the measured output to be as well. Okay, right now when it settles, so here's time across the x-axis, here's the measured output, we're at 90. So we're pretty far off. That's a pretty bad design. Okay, that's bad news. What do we have that's good news here?
Stable.
Yeah, stable. And what else besides being stable? Quick. Okay, these are typically the 3 most important things we think about. The 4th thing, which you might also want to think about, is something called overshoot. You see that bump there? You might be concerned about that as well. Okay, so design problem's pretty easy. We've got a number between, well, actually between minus infinity and plus infinity, somewhere in there. Okay, so let's work our way through this a little bit. Okay. Would it be a good idea to set that parameter, that Kp, to something negative? No. Not, well, yeah, even worse than that. When you think about it, just the semantics of this max users thing, what's it going to do? That means that if you don't have, so if it's if the measure, if that control error there is positive, that means you have fewer users in the system than you'd like. And you use a negative value for the constant. That's going to mean I want to reduce max users. You're going the wrong way. Okay, so we figured out that semantics pretty well. So it's a non-negative number. Could it be 0? Why wouldn't we want it 0? Not going to happen. Nothing's going to happen. Right. Okay. So now we've cut our design space by over half. We're almost there, guys. All right. So it's a positive number. All right. Okay. So should we make it bigger or smaller? We see what the value is at 1. Bigger? Pick a number.
1.3.
1.3. Okay, 1.3. All right, so tell me about this. Seems sort of like another good news, bad news situation, doesn't it? More overshoot, right?
Slower overshoot.
Right, getting closer to being accurate, a little bit slower, overshoot. Okay, next suggestion. Let's focus on accurate for right now.
2.2.
1 over 4.43.
All right, let's see. Let's try. I heard a 2.2. I'll go with that one for right now. All right, so you can see the trend.
When you want the system to determine this to a filter?
Okay, so let's try. I heard a 3. Let's try 3. All right, and let's be a little bit more dramatic. Let's do 4. Okay, look at the scale. Okay, so we've actually become unstable. Okay, so what's the intuition here when we got to the point where it actually became unstable? When think about it, what happens is what this constant is controlling is how much of that control error, the thing that's the difference between what we want and what we get, how much of that we're going to actually react to. The bigger that constant, the bigger our reaction. Okay?
That reaction is swamping our actual data?
I'm sorry?
And so here the reaction is swamping our actual data?
Exactly. Right.
You want it to go down over time?
I'm sorry, what is that?
Go down over time?
Yeah, you want it, right. This is unstable. I mean, a real system wouldn't actually become unstable. What would happen is that, something would break. I mean, you'd run out of memory or something like that. I mean, it wouldn't go on indefinitely like this. You might get wild oscillations, but you wouldn't get something that grows forever. I mean, nothing can grow forever. So, but it's clearly something that's undesirable. Okay, so I mean, you can play with it a bit, and then just get to the point where this one's still unstable, and you can see that that's still growing. Keep on going down, and find points at which we're getting closer. But you can see also what the trade-offs are as well. So this was the part that was, just a second, I'll get to you. This is the part that sort of sparked a lot of interest for us, because it seemed like we were getting at some of these issues of potentially looking at trade-offs. We had a way of talking about time, because this K thing in time, and see what it is that happened over time. We saw this notion of the importance of being able to converge quickly, the issue of overshoot, and then this issue of accuracy. So those elements seem to play together very nicely. Okay. Just 1 second.
So, talking about models, right? Some of the models are useful. How do we know this model is useful? I mean, it's true that system cease to oscillate, but that assumes what the model we're having here actually models the real system. Maybe this real system will act differently on the...
Okay, so the question is, how good is the model to relate to the real system? I'll show you some examples where we compare the real system to the model, and you'll get a feeling for that. I'm not saying it always works as well as what we found, but it worked pretty well. So for our cases. Go ahead, Hassan.
So there's something a little counterintuitive to me here, which is the fact that the change here is irrespective of what the frequency of K is. So the intuition that I would have, for example, is if we adjusted faster.
Okay, we're using constant control intervals. We're not changing the control intervals.
Yeah, but you're not specifying what the constant...
No, I didn't specify that. I just said it was the same.
Does make a difference.
Oh, yeah, absolutely. I mean, that's a whole other element of the design, is to figure out the control frequency. Yeah, right. Yes?
So you probably cover it later, but the jobs that they go through the system, you don't know when they start execution how long any given job's going to take. And so you're sort of controlling based on what happened before, which not necessarily predicts what's arriving now.
Absolutely. I mean, that's an inherent issue, depending on the limits of your measurement system, is that you really are making your decision based on the past, potentially based on some limited understanding of state, depending on your measurement system, and then that has consequences in terms of things like how accurate your control is, whether or not it's stable, all those other factors, and that's part of the analysis, the control analysis.
Same assumption as the exponential decay, right? Because
Yeah, that's why I think you have to have the filtering and everything, because you have to respond to these changing loads. Otherwise, you're not a stable system.
Well, and those are trade-offs as well. When you see, we get to the examples later on today, the introducing filters tends to introduce some more delays, too. So, I mean, that's all part of the control design problem. Okay, so let me get back to the slide deck here. Yeah.
This is a very basic question. I'm sure I'm missing something very obvious. Why would a YK be different than UK? In a stable system, shouldn't be the number of users coming into the system be equal to the number of users out of the system?
So the number of users, oh yeah, over time, you're absolutely right. If at steady state, the number that come in can't exceed, have to equal the number that are going out. Otherwise, you're not in steady state. But this is an important distinction in why being able to have some analysis of dynamics is important. At any interval, there may not be a match. You may have more coming in than are going out, or more going out than are coming in.
I think there's some queuing involved at the server layer.
Oh yeah, absolutely. There's queuing internally. And in fact, this equation right here, the fact that you depend on previous state, the reason for that is there's queuing.
And just one thing, last thing. That feedback loop that you have going up from the server back to EK?
Yes.
That is just an indication of that we are using that input to calculate EK.
Yeah, right. What it means is, right, it reads what's there as part of the decision making for the controller. That's what it means. Yeah.
So I didn't understand why YK would be the same as UK in a stable state. If UK is the number of users in and YK is the number of requests out or something.
Well, I may have misunderstood the way I interpreted the question, which may have been the wrong question, so I apologize. The way I interpret the question is the number of users that go into the system have to equal the ones going out at steady state. Yeah, requests coming in have to equal requests going out at steady state. Otherwise, the system is not stable. That was my interpretation.
Wait, are you treating the number of users as the number of requests?
Yeah, the better way to look at this is to look at this as request. To have this discussion on stability is to talk about requests coming in and requests going out.
All of these numbers represent.
Okay. What we're talking about here, though, I mean, this was a discussion of stability, right? Right. Okay. What this system does is it's regulating the number of RPCs in system. The RPCs in system are related to requests that are coming in, requests going out. That is not part of the design of this controller that you see here. This controller is regulating the number of users. It's not regulating number of requests.
So we are using two metrics in this model: number of users and number of requests.
Okay. The requests obviously are there because a user came in.
Sure.
Right.
I think what we're asking is what are the units coming out of these three functions?
Okay, fair enough.
U and K all return units mode.
Okay, fine. This is in users and this is in users.
Yeah, okay.
Right? Okay. Now, I think there were two separate concepts going on here. One is what's the definition of stability of things going in, things going out, and then what are the units here?
So I guess I don't understand what it means to have a user coming out of a server. You know, if I imagine that server, okay, great, I've got SQL requests coming in and disk requests going out. That I can imagine this applying to. Is that the kind of thing you're...
Right, so what comes in here is, let me go back to the previous diagram, because this is the control diagram, not the, yeah. This is probably maybe a little bit easier way of describing it. So here you see users making RPC requests, and the flow, you've got a flow of RPCs in and a flow of responses going back. And I think that that's the request side that we're talking about. What happens over here is if we look periodically at the state of that server, there's a certain amount of queuing that's going on or concurrent processing that's happening. And that's what's being regulated by this max users. And the way it's regulating it is it's affecting the flow of users coming in and users going out. Does that make more sense?
It might help to... Well, I may be confused about this.
Okay.
When you say the number of users coming in, are you preventing users from logging on, or you're preventing requests from coming in?
We're preventing their requests from
that
coming in.
Helps, I think.
The other thing I was going to maybe note is that other diagram, the feedback and the arrows, that doesn't indicate a request flow. That indicates a sample, a measurement of the number of users.
Yes, it was just the notion of, what we're regulating is we're actually regulating the number of requests.
Are we? No,
What we're actually regulating is admission control. We're actually regulating, it's
not the actual work request.
Yeah, it's admissions, right.
So you're actually using the connection to limit the total number because there's some smaller percentage of actual work being generated than there is connections.
Right. So what happens is before a user can, on the user's first request, they have to be admitted to the system. So they make that first request. They either get admitted to the system or they don't. If they don't get admitted to the system, the request does not flow in, and essentially they see something like server busy, or they get some sort of busy window.
You can think of it as max connections in Exchange, right? Then the maximum number of connected users.
Then I don't like the addition, because I don't let my daughter add two things that have different units.
Okay. Well, what are the different units here? So we've
next page, but
okay, fair enough.
Yeah. Yeah, U and K, Y and U on the right.
So Y, okay, so U is, okay, these are not being added.
On the right they are. System model.
Oh, these, right, okay, over there. Yeah, I mean, that's part of the implication. There's a conversion that happens as well, right.
I just think that's the source of some of this.
Okay, no, this is fair. And actually, but let me just pause for a second. So the reason why I'm spending time on this is that what we're discussing right now, this translation from a software system description into a control diagram, is, in my opinion, the hardest part about applying this stuff. To get to this diagram and these equations, it took us well over a month of intensive work. And we ended up coming with something fairly reasonable, but all these discussions are the kinds of things we went through. Okay.
So I'm coming back to his question, maybe some discussion here, and I'm assuming the system, just to make sure everyone's on the same page, that UK and YK are the same thing. In other words, maybe in order for a user to do work, it has to always log in the system, do a piece of work, and then log out, and then so on and so forth. So in other words, max users and RAS is the same thing. Assuming that's the case, in steady state, UK and YK are the same, right?
UK and UK.
No.
UK and YK.
No.
The only thing that has to be the same is the input, the R, the desired number of whatever you're measuring in Y. Those units have to be the same.
Right. Exactly. That's the only thing that has to be the same.
So you could be your decision to admit the request or not.
Right. So assuming
and Y is the number of users.
So assuming I want 200 units of work to the system to perform at all time, my input to say I want 200 and the system performs 200, then that's
it doesn't work though. It's like it's admission control because it depends on the number of users present. You could set it at 200, but if you don't have 200 users out there, you're not going to get to 200.
Okay, so then I don't know what to express this. So what I'm trying to get is that outside of the normal steady state, what that formula is trying to cover for is not the steady state, is the variations from the steady state.
That's exactly right. This is about dynamics.
So in other words, kind of going further, this formula is trying to account for the randomness in the system, I don't know how to express it.
Well, the variations that occur, they could either, from other sources.
So now, if this is the randomness or some factors that will bring the system outside of the steady state, that randomness, that external factors that is essentially non-deterministic, so to speak.
Right.
How can we know that the system will be stable? How can we?
So what? Right. Well, okay. So I think what I'm going to ask you to do is hold on to those thoughts, and as I go through the rest of the presentation today, see if at least part of that is addressed. Because part of this is a matter of we're using some simple models to deal with a variety of factors. Some of it is randomness, some of it is uncertainties about exactly how the system behaves. And the point is that by going about it this way, we at least have a systematic methodology, which is akin to what other branches of engineering do. Because they deal with exactly the same set of problems. I mean, it's not software. It may be a turbulent fluid flow. It may be a propeller motion. It may be a milling machine. But the issue of uncertainty about how the system behaves, randomness, external factors, they all come into play. Okay. All right. So let me... all right. So what we ended up doing, to give you more of a flavor of where this can go, is... we worked closely with the database management group and introduced a couple of features. One of them was really a regulation issue dealing with controlling background work, something called utilities throttling, dealing with things like backup, restore, rebalance kinds of stuff. Utilities that are important for maintaining the integrity of the database system, but they also have a severe impact on production throughput. And the second one had to do with more of an optimization problem, dealing with balancing memory pools. And so all I was trying to do here was to show that there were some real-world implications. I'll go over these more later on. And that the 59% is sort of like, a researcher's dream. But it was much more like we could demonstrate some real effects. 59% is very high. I mean, there were some substantive effects, but it wasn't... The overall conclusion was not 59%. Okay, so this one really just summarizes some of the discussions we've had already about the importance of stability, accuracy, settling time, and overshoot. And so I'm not going to dwell on that right now. So now that we've had the introduction, and you have more of a feeling for what this is about, the kinds of things we're going to study, in essence, the work that we did with the spreadsheet and this ability to then talk about what should the value of K be to achieve the right level, an accurate kind of regulation with something that's stable and short settling times. That's what we're going to be talking about today and provide the sort of the mathematical background to do that. I found, is there anybody here who's already, I know Mario's has a background in control theory, and I think Hazem, you do too, a little bit. Anybody else have a background? Okay. So a couple. I'm sorry?
Took a course.
No, that's background. That's background. Okay. So what what I'm going to do is I have found, from my own personal experience and talking to others as well, that while a lot of these techniques could be really useful to us in designing software systems, the way it's presented in existing textbooks makes it really daunting, because right away you're presented with differential equations and Laplace transforms, and all the examples are mechanical examples dealing with dash pots and other things that you have no clue about how relating this to anything meaningful in software. And I think one of the things we were able to do over time is once we finally understood through our thick skulls what control theory was about, we were able to sort of trace our way backwards and say, okay, here's the subset that software people should know about, and here's a way of presenting that material so that they can understand it. That's what I'm going to try and give you the core of today, that kind of presentation. To use this, there's some tools that you need to use. There's something called MATLAB, because what you end up with is basically some polynomial expressions that you have to figure out where the zeros are in the denominator. I'll explain what that means in a second. But what it ultimately that's going to relate to is whether or not the system is stable and how quickly it settles. And so to really use this, you're going to need those tools. But let's at first get through what the theory is, so you understand what that is, what the basis is, and you can say, geez, this is far too simple, I don't believe it, or hopefully you can take a little bit on faith that we have been able to use this even as simple as it is, and then say, gee, let's see if we can extend it. So that's really what the class is about today. Get to the point where you understand the theory and can use it for some simple cases. Okay. So we've pretty much gone through this part here. The basic elements in the control system. So you've got the target system. We saw the Lotus Note server. And the key things to think about are, what is it that you can manipulate, like that Max users? We spent a lot of time playing with this. This is where most of the system investment goes, is to figure out, get the right control inputs over there. And then the measured output over here is, how do you get reasonable sensors coming out? And those two factors can involve considerable investment. The advantage of sort of the control theory mindset in this is you realize the importance of delays on either side. You can imagine a car with a braking system where there was a delay of a half a second between applying the brake and the car beginning to stop. You know, that's the kind of thing we have to be careful about when we introduce controls of various sorts, those kinds of overheads. So, and then similarly on the measurement part, you know, if you couldn't see the effect fast enough or sense the effect fast enough, like the problem we ended up having with the Lotus Note server. I mean, actually, when we did our initial control design, we didn't even take into account the fact that we had this log kind of instrumentation system that we didn't even see the number of RPCs in system until it had been written to the log. And that uncertainty in state meant that if we had a large value of that k, then we tended to overcompensate. We actually ended up with instabilities. So, I mean, we could see it because we got these wild oscillations. It didn't grow forever, but it certainly wasn't desirable. The other element in this system that I have not discussed, which is very interesting, it will hopefully come in later on when we get to some of our examples. And when the last part of this class is sort of a work group where Mario has some stuff that he's done with Hotmail, and staff has sent me some material about singularity. And I think what I would like to do is then use these as sort of case studies to say, okay, how far can we get with a control design? In Mario's case, he's actually done some degree of an implementation. In Stathis's case, I think he's trying to think the problem through and have some initial thoughts. It'll be a fun thing to sort of interact about. But one of the things that comes in there that becomes sort of important is, what about the case where what we want to control is, let's say, a response time? But we really don't have direct measurements of response time in our target system. Suppose instead of response time, we can measure queue lengths, and we can measure transaction rates or completions. Now, maybe with the two of those, we feel comfortable with an estimate using Little's result and just divide the queue lengths by the completion rate. Say that might be an estimate for response time. That kind of calculation is what's called a transducer. And it introduces potentially its own dynamics, because Little's result applies in steady state, but if you're doing this in short intervals, you know, how accurate is that? Okay, so let's see how well this part works here with this group. I'll skip over this if it isn't. It was great for a class at Columbia University, but maybe a little bit less. Maybe. Okay, so this is a simple example of control design. Okay, so what you got a classroom, and it's winter, heat's on, and the question is, okay, so the instructor doesn't want the students to fall asleep, doesn't want it to get too hot. But you also, and the idea is that once people start yawning, they're consuming a lot of oxygen. So I can make them yawn less by raising the window. But then if it gets too cold, nobody wants to stay in the class. Okay, so that's our environment, our control system. And so the objective here is just to give you a flavor in some very simplistic sense of this mapping of a problem into this control design thing. So remember, we got these control elements. We've got the system, we've got the controller, we've got a transducer, we've got a reference input. We want to figure out all those things for this simple kind of environment. Because this is, to be honest, this was one of the hardest problems, one of the hardest parts we faced when we were actually applying this stuff. Okay, so this is the way the system works. You open the window, you get air, you get awake students, close the window, everybody's asleep. Okay, fine.
I thought you were going to say that people were yawning in class.
Yeah, well, that's true. Okay. All right, so here's our system. Here's the control architecture, at least. Okay, what we want to do is try and figure out for this simple system, what are each element of this control here. Okay, so what's the target system? What is it that, the thing that we're controlling? The people who are yawning, or so it's sort of like the...
Really? It's the number of people in the room.
Well, the number of people in the room is probably not changing, hopefully. I mean, if extreme case, that's the instability. People leave or die or something, right? So we're trying to, okay, so we're certainly, I think a measured output is certainly the yawning rate, right? Okay, and we've got the students there, and we've got the windows and the students combined, yeah.
But you also had maximized temperature there. So where is that measured?
Well, okay, that's an interesting one. Okay, so in this case, the way I would look at this is that, and it's sort of like this, the following logic. If I want to control the yawning rate, I want to maximize, basically it's a constraint problem, so I want to maximize the temperature subject to a constraint on yawn rate. Okay, so how do I maximize the temperature? I keep the windows closed as much as I can. Okay, so once I hit that yawning rate, that's the constraint yawning rate, there's no point in going any lower, because if I go any lower, the way I get the yawn rate lower is I open the window more. So the observation here is that by achieving the regulation objective, I'm also achieving the optimization objective. That's the logic.
Because otherwise it turns into like the range of optimal control.
Exactly. So we're not, and that's actually an important observation here, because in computing systems this is a really, really common situation where we want to maximize throughput subject to some constraint on response time. And the observation is that typically if you make it as close to that response time objective as possible, not lower, because then if you make it lower, you're probably going to constrain throughput in some way, because you're giving more resources available so that transactions have more capacity available to them. If you make it too high, you're not going to meet your constraint, and that's the logic here. Okay.
Is the yawning the measured output?
Yes.
Or I think is the measured output is how many people are in the class that are like pay attention to, because otherwise if the yawning...
In this system, you're designing a different system. In this system, yawning is the measured output.
If yawning is the measured system, then we can open all the windows.
No, but we could, but then we have not maximized temperature.
He's throwing in the temperature just so to say that, yeah, you don't want the trivial solution to be open the windows.
Yeah, exactly.
He wants to control the window. You want to keep people comfortable, but as soon as you see some yawning, open the window. And if you see more yawns, open it more. And too much time goes on and nobody's yawning, lower the window until...
You're right. I was thinking not the measured output. I was thinking about the goal of the system, which is from the measured output.
Yeah, Mario.
What about how often do you measure the output?
I haven't talked about time here. I mean, that's another important consideration, and the whole issue with sample frequency and control frequency become separate design problems as well. I'm not going to really dig into those much here, but you're absolutely right. That's important. Okay. All right. So target system, I think we sort of have a loose understanding of that. That's probably the windows, and the windows are sort of like the actuators. That's sort of part of the target system, and then the how the airflow affects the students is in the center here, and then the measured output is a yawning. What about the controller? What's the controller here?
Person at the window.
Yeah, it's a person at the window who's actually making the decisions and looking at the difference between the desired yawn rate and the actual yawn rate, and then figuring out, should I raise or lower? And if the yawn rate is too high, I'm going to raise it. And if it's, if it looks like we're getting below our objective, you can lower it so that we can maximize the temperature. Okay, so I'm not going to dwell on this in detail, but the thing that I want you to come away with here is a discussion we had right now, which is this is an absolutely trivial example, right? I mean, it's a silly little thing. So now you're designing a resource management system in a complex environment. Trying to figure these things out is a little bit of a challenge. It takes a little bit of practice and some playing to figure it out. All right, so the next little bit is really more about this, about making sure that you've got all the elements of the system. So I mentioned before the issue that we face, that when we did our initial control design, we designed for the server, but we didn't consider the sensor. And that's an important part as well. And your view of the system as a software architect is going to be in terms of flows through the system, flows of requests through the system, flows of data through the system, translation, for example, from a SQL request to disk I/O requests and CPU requests. But the control perspective is a little bit different. The control perspective looks at it in terms of the things that you're regulating. And so that's another form of translation that takes place. What I'm going to be talking about over the next little bit is closed loop control, where you have a measured output of some sort that is then used to make control decisions. There is also, and this is more widely used in capacity planning especially, notion of open loop control, where you have a much smarter controller and it's able to figure out what it is you should use for your control set. I mean, typically for capacity planning it's like number of servers or network bandwidth, things like that. So it figures this stuff out based on more sophisticated models. There's no feedback in open loop. And that's a huge advantage in terms of these issues about settling time and stability. The problem is it requires a very accurate model of how this target system behaves. And that's real hard. And so that's why, to a large extent, we can potentially get away with really simple models because we constantly see how the system is actually operating and we can adjust and react. And the other thing is a capacity planning system or some other open loop system has to consider all the complex nonlinearities that might happen with different values for configuration and workloads and the like. Whereas potentially a control system, since it's operating over time, really all it has to do is work in that region where it has some range of control for that particular workload. As long as that's relatively smooth, it's potential that a linear approximation is okay. Now, that's not always going to be the case. I mean, systems do go over the edge. You hit a memory threshold where suddenly you start paging. You know, you didn't predict that through any sort of linear system. But it can work pretty well in many cases, and you just have to guard against those nonlinearities. Yeah?
Would there possibly be multiple inputs in the open loop case, so in the sense that the plant is subject to other environmental inputs?
Absolutely.
The open loop controller can still read those.
And this is a simplistic diagram. You're absolutely right. The question was, could there be multiple inputs in the open loop case? Absolutely. And actually also in the closed loop case, there could be multiple inputs as well. Right. But I mean, it's all subject to, of course, the issue about how accurate is your data over the time frame that your time horizon that you're forecasting. All right. One other sort of terminology thing is this issue of type of control. What I've been showing you is something called regulatory control. It's like a thermostat or a cruise control. You set the mark, and then the system tries to do whatever is needed to adjust for that. So in cruise control, you brake or you accelerate. In a thermostat, the furnace either goes on or it shuts off. In computing systems, I mean, this is definitely interesting to us because we have like QoS management kinds of situations where you want to hit certain response time targets. So that's definitely interesting. But from a control perspective, the change in that reference input, which is essentially a policy, what different classes of users have different target response times, those reference inputs don't change very often. And if we're talking about a design that focuses on measuring the effects in terms of stability and settling times of changing the reference input, it's probably not a very exciting problem for computing systems because you just don't change it that often. But there's a variation on this problem which is very interesting to us. And that is something called disturbance rejection. That is, I still got this regulation problem where I'm trying to hit QoS targets. The difference is that now I've got something that's affecting the relationship between my control input, like max users, and my measured output. So for example, there are workload variations. That might be something that we're concerned about. There's a lot of dynamics that are involved there, and those things, being able to respond to that quickly and not go unstable, I mean, that would be very important. The other thing to happen are system failures, and that's another thing that will affect the relationship between the control input and the measured output. So it's really more disturbance rejection that we're formally interested in. The key observation is, though, that as we look through what the theory I'll present provides us with, it turns out that the way you design for disturbance rejection is pretty much the way you design for the regulatory control. So it's not going to make, I'll present the problems really as regulatory control, but understand really what we want is disturbance rejection. Yes?
How is it different from how stable the system is, or like how far the system converges and stays there? Is that the same thing?
Well, okay, so you're talking about what are the characteristics of a system that would be desirable in terms of controller design?
I mean, is disturbance rejection the same thing as regulatory control, for which the controller is designed specifically to
Okay, disturbance rejection is not about controller design. It's about a nature of the system itself. A system in which there's something that's going on that's going to affect the way that system behaves. In other words, it may be at some point you set max users to 100, and you actually end up with 100 users of the system. Another time, you may end up with something else altogether. It may only go up to 50 because they're very long-running users. And just as ones die off, new ones are not coming in. That's what disturbance rejection is about. But in terms of design, and what you'll see is I'll largely phrase it this way in terms of our examples. The last one, which is a bit different, is optimization. And in this case, you don't see a reference input. So it's not a policy per se. It's sort of built in, and what it means is that there is, you want to try and get the best you can. So that's a pretty common one for us. I mean, we'd like to get the best response time we can, the best throughput you can. Typically, if you do this in a general way, it's a very complicated control design problem. The good news is that for computing systems, there's one sort of special case that's really, really important to us that allows us to translate this back into regulatory control. And that very important case is load balancing. Because we know from basic queuing that your response times are largely determined by the bottleneck resource. So that's the one that's most heavily utilized in terms of your path through the system. And so if you can make in like a clustered environment, you can make it so that you have balanced servers in the cluster. They're utilized about the same, and this is a complex problem because there are different kinds of resources, and you have to assume that there's many elements here. But I show you, for example, in our DB2 example for memory, and we were load balancing memory pools, and that seemed to work fine. But what that means is that by regulating those resources so that each one moves to the mean value, the bottleneck has reduced to everyone has the same level of utilization. So that one particular case is something we can address through regulatory control. There may be others. I mean, that was one that we used. Okay, so the properties of control system, I think we sort of went through this. We're certainly interested in stability. That's sort of graphically displayed here. Make sure we're all on the same page in terms of what it means for the other properties here. So let's talk about accuracy. So this is just an illustrative plot over here where the x-axis is time, the y-axis is some measured output like RPCs in system. We see over here, this is our target, this R sub SS for R steady state. That's what we would like to have. Y sub SS, or Y for steady state, the dashed line, that's what we actually get. The fact that the dashed line differs from the solid line means we have an error or it's an inaccuracy of some sort. Whether or not we care about it is another story, but that's sort of the definition of this control error term here. The settling time is the time it takes from whatever you're looking at, like maybe there's a change in workload or a change in policy, until you get really close to whatever the steady state value is. Typically in control systems they use like 2%, within 2% of the steady state value. And that's what we use as sort of our rule of thumb. So our settling time here would be about 9 time units. Overshoot is the amount you surpass the steady state value before you actually you start coming down. In and of itself, it's probably not terribly interesting. The reason why I think longer term it becomes more interesting is because when you overshoot, you also tend to undershoot. And so there's some measure of oscillation there. To be honest, the ones that we mostly were interested in were these first three. And really stability and short settling time are very much connected with one another, so that you actually in the end just sort of focus on those two.
Do you find systems where the overshoot can send the system into a different state, and so
absolutely right.
Your risk?
Right. And that's part of the design consideration. Absolutely. Yeah, and this is actually sort of leads on to an interesting side point that I want to underscore in terms of how you use these kinds of techniques. Because these techniques provide you with exact mathematical answers to a problem that you may not care about. Okay, and that's one thing you have to watch for here. So you have to be careful about what it is that you're designing for and understand the limits of what these models are. So you could get a model that'll tell you what your settling times and what your overshoots are, but you have to be aware of the fact that there's a certain chance under certain environments where you're going to go into you're going to overshoot, and then at that point it's not going to matter, because at that point you're paging and everything is going to go down quickly. So thematically here, and the way we use this with the product group at IBM, was we said, look, we can give you certain kinds of analyses in special cases and then some general framework. Let's figure out which one of these you care about. And then there's a lot of engineering. It was very useful, but there is this interaction here, and I'm not going to claim that you just plug it in and then you go. Yeah.
You said 2% was what we would consider to be within stable state. What causes it to, you think that it's unstable? Is it just...
Oh, no, not stable, steady. Steady state.
Steady. Well, but we know that the system is unstable when we look at the chart. And
yeah, this chart over here, this is unstable because it rises without bound. Right, basically, or it oscillates in extreme ways. This one here is...
Is there a mathematical thing you use?
Yeah, there actually is a mathematical definition. There's something called bounded input, bounded output systems. And there's a formal definition and description of this kind of thing, but really for our purposes, what we're concerned about is really something that changes so much in reality that we can't use the system. I mean, that's sort of the practical implication.
It's stable and yet fail to sort of settle into a...
Absolutely, you could oscillate. Right, and controller-induced oscillations is one of the things to be very careful about. Because we'll get oscillations because of stochastics, but the controllers themselves, because of the feedback, they can introduce oscillations, and that's probably one of the most undesirable characteristics you can have of a system. I'd rather have it be slow than highly variable.
Is there a way to estimate the frequency of the...
Is there a way of estimating the frequency of the oscillations? Yeah, there are techniques. It's not something that we really dwelled on. It wasn't as important in our designs, but it may be in other environments there are. There were... I'll give you one example where the oscillations were something that was a clear design objective in the work that we did with the DB2 buffer pools. There was a lot of concern about oscillations in terms of moving memory from pool to pool without really changing much, because this is consuming disk bandwidth, this is introducing additional latencies. So that actually was an important part of the design. Okay, now I don't have the... If you can get me the copy of the slide deck in the back of there. I'm trying to figure out when our break is. I think we have a break at 10:30. Oh, okay.
Through 10:30. 10:15 to 10:30.
Okay, so 10:15 to 10:30, so we're right at break time. Thank you very much. Okay, very good. Thank you. So I think I'm probably a little bit behind. That's okay. Let me see what the... look back at the slide. I want to see where it is that I wanted to be. Yeah, so I'm probably... Okay, that's fine. We'll work it out. Okay, I think there's just a human limit here. So why don't we go ahead and take the break now, and then we'll come back and continue.